Hello everyone, welcome back to today's class. So, today we will be continuing discussing on catalytic cyclopropanation reaction. In the last class we have just introduced the topic. Today we will discuss more about it and mainly the asymmetric version as well as some industrial application of this catalytic cyclopropanation reaction. See, the cyclopropanation reaction is nothing but creating cyclopropane ring from an olefin. Traditionally, it is done with carbene. Now, if you have an olefin and you are reacting the carbene equivalent with it, one would expect then to form a cyclopropane ring. As we have seen that palladium catalyzed methods are usually used, where diazomethane is the starting material from which palladium carbene is forming. On the other hand, also it could be possible that rhodium or copper be used for such processes. Usually for rhodium and copper, we do see diazo esters are used as starting materials. Today, let us try to look at the cyclopropanation reaction in more detail and let us try to discuss it along with its mechanism. At first, we will look at one of the example and then how the metal carbene is forming from the diazomethane or diazo ester, and then how they are being utilized for this cyclopropanation reaction. We are going to discuss that. Okay, let us discuss cyclopropanation. Usually from a carbene, what we see that it is reacted with olefin to give the cyclopropane ring, and of course, in these two center you can set the stereochemistry. Often we will be talking about the diastereoselective synthesis for such compound. The common catalyst that is used for this purpose is palladium 2 for diazomethane as the starting material, rhodium 2 for and copper Y 1 for diazo ester, that is nothing but this reagent as a starting material. Now, also it becomes important how these reactions are working. We can have presumed intermediate for these cases, which is nothing but a metal carbene equivalent. Of course, that is what is forming, but how it might will be forming, let us look at from the diazomethane one. So, CH2 minus and N2 plus, what you might will get in the process is M minus CH2 and N2 plus reagent. Overall, you end up getting MCH2 plus, of course, N2 comes out from these reactions. So, what we have seen right now is diazomethane reacting with metal to give the metal carbene intermediate. Of course, one would argue maybe it is the free carbene that is doing the chemistry. Can we have some sort of mechanistic proposal or mechanistic proof evidence in support of metal carbene formation? Of course, nowadays there are a lot of study been done. We will discuss the first example where such metal carbene formation could have been possible or some evidence has been gathered in favor of metal carbene formation. Let us look at one more example to discuss this metal carbene as the reactive intermediate for these cyclopropanation reactions. Okay. So, the one examples that would like to discuss is where you have a chiral enantiopure auxiliary along with the substrate. Okay. And now, with this substrate, if you are taking a propene or the olefin double bond, what you would expect in presence of diazomethane and palladium acetate to as catalytic amount, of course, to form in presence of the chiral auxiliary. Chiral auxiliary is in here, this is the chiral enantiopure auxiliary, and from there on you would imagine to form a cyclopropane ring, because this CH2 is coming into picture, and overall you get the product that one would expect. Now, in this case we get 93:7 diastereomeric, so therefore 86% DE, which is quite interesting for such reactions. Now, still one would argue for these reactions, how this reaction might be happening, what would be the procedure. Is it the free carbene that is forming, or the metal carbene intermediate is generated during these reactions? In order to prove that, or the first evidence that came forward for such involvement of a metal carbene intermediate is the one where copper is used. Let us try to look at the first example where metal carbene could have been proposed, or the evidence has been gathered in support of metal carbene intermediate for the cyclopropanation reactions. So, the first example of homogeneous reaction, homogeneous transition metal catalyzed enantioselective reaction. Okay. The one example that comes into mind or in the literature, that is the diazoester reaction in presence of copper catalyst to give the cyclopropane that one would expect in this case, and that is this reaction. Now, still even if you are getting this product cyclopropane, that does not mean that it is involved the copper carbene as an intermediate rather than free carbene. Perhaps one way to prove that, at least that was the first evidence gathered in favor of metal carbene, is if you add a chiral ligand, if you introduce a chiral ligand for the metal center, in this case for copper, can we get any enantioselectivity? If you get any enantioselectivity during the process, it could be suggestive of the fact that metal carbene is forming. If it was a free carbene, you would not expect any enantioselectivity during this reaction, during the reaction what we have just drawn. So, if any EE is there, then one can argue in favor of a metal carbene species being the reactive intermediate for the cyclopropanation reaction. Let us look at what has happened in presence of the carbene as a in presence of a chiral catalyst used for these copper catalyzed reactions. What if it is via a free carbene? The free carbene that you are expecting is this one. Okay. So, this is your free carbene, or whether this is forming copper carbene intermediate is forming. Now, of course, this you can name as copper carbene, right. This is done by Nozaki, by the way. Now, a chiral ligand L star is used, a chiral ligand is used. What was observed is a modest, very modest 6% EE. So, this is the reaction that then proposed that since in presence of a chiral catalyst, one can achieve some sort of EE, although very modest at best, but still this is suggesting that carbene is involved, metal carbene is involved. It is not the free carbene that is doing the chemistry. Indeed, the metal carbene is the intermediate that is involved for the cyclopropanation reaction. Okay. Now, let us try to look at one of the examples where it is used, the cyclopropanation reactions are used in industrial scale, and therefore, one can justify the importance of these processes. Indeed, in medicinal chemistry, lot of these cyclopropanation reactions are used quite routinely. Okay. Let us look at one of those medicinally important or medicine that is utilized or produced by these cyclopropanation reactions. So, industrial application. In industry, this is a reaction which is quite popular, where diazo ester is used in presence of a copper chiral catalyst to get this intermediate, which is an advanced intermediate for the drug that all of us are familiar with, that is in the market, that is called the cilastatin. Okay. This is the structure of cilastatin, and as you know, cilastatin is used as antibiotic in conjunction with carbapenem, which inhibits the enzyme dehydropeptidase. Okay. This is the cilastatin, where we are synthesizing by the cyclopropanation method, and once again this is used as in conjunction with carbapenem to inhibit the enzyme dehydropeptidase. Okay. So, these are antibiotic combination. Now, so this is again cilastatin. Now, of course, this is utilized and used and synthesized in multi-gram scale, or rather kg scale. Cilastatin is a active component of the antibiotic. Now, by this simple cyclopropanation reaction, the main stereochemistry is set, where we have seen that this copper catalyzed chiral copper catalyst is used for this cyclopropanation reaction. Right. From there it can be further modified to get the cilastatin compound. Now, of course, in addition to cyclopropane as the material, one can think of cyclopropene preparation. In those cases, as one would expect, we cannot use olefin, right. We must use alkyne instead of olefin if we are to get cyclopropene by similar method that we have seen for cyclopropane reaction. Okay. Let us try to synthesize cyclopropene ring, which is of course is much more unstable and compared to cyclopropane, how cyclopropane can be propene can be synthesized by utilizing the same technique. So, let us just directly discuss asymmetric cyclopropanation reaction, cyclopropenation reaction, cyclopropene ring formation we would like to discuss. The reagent, as we tried to discuss, we need is a alkyne and let us say for example diazo ester, or rather amide, let us say for example, and a chiral rhodium catalyst in this case is used to give the cyclopropene. I hope you can appreciate this method for this cyclopropene synthesis. As you know, cyclopropane ring strain is nearly something like 25 or 28 kcal per mole, and cyclopropene is nearly 50 to 60 kcal per mole. Okay. So, this is very strained molecule cyclopropene compared to cyclopropane. So, overall in this part what we have seen today is the cyclopropanation reaction, and then expanded the cyclopropanation methodology for the cyclopropenation reaction, which are even more energy demanding, and usually it is much more difficult to stabilize and prepare the cyclopropene, but the rhodium, for example, a rhodium catalyzed even asymmetric version of this catalyst can be prepared by utilizing simple carbene type of chemistry. Okay. Both the cyclopropenation and cyclopropanation reactions utilize carbene or metal carbene, to be precise, as a reactive intermediate for these reactions. We have seen some evidences in favor of metal carbene as the reactive intermediate as opposed to the free carbene for these cases. These small molecules cyclopropane and cyclopropene are indeed very important structural building block for pharmaceutical or even for other industrial use and of course, for academic use as well. So, in the next part we will try to discuss the carbon-carbon various carbon-carbon bond formation reaction. Okay. Of course, a carbon-carbon bond formation one can think of by various approach, but most often when a difficult carbon-carbon bond formation is talked about, for example, sp2-sp2 bond formation reaction or sp3-sp bond formation reaction, sp-sp3 bond formation reaction, sp3-sp3 carbon-carbon bond formation reaction. These reactions are extremely challenging and therefore, actually there exists no other organic transformation that can do it except using the organometal chemistry or organometallic intermediate. So, organometallic intermediate has kind of revolutionized the way these carbon-carbon bond formations are looked at. Nowadays, it is indispensable to synthesize pharmaceuticals, industrial other molecule, different academic purposes, wherever you can think of synthesizing or introducing a new carbon-carbon bond, usually the first thing that comes into mind is the organometallic chemistry, where organometallic intermediate is doing wonder to do these carbon-carbon bond formation. Let us look at some of those examples, how one would be thinking to prepare it both in industry and in academia. That would be our next part of the discussion. Okay. So, palladium catalyzed, first we will discuss the palladium catalyzed method. Of course, nowadays not only palladium, a number of other metals have been used for these carbon-carbon bond formation reaction, since historically and overall expansion wise palladium played a key role for these difficult carbon-carbon bond formation reaction. We will try to mainly focus on the carbon-carbon bond formation utilizing palladium as the reactive intermediate. Okay. So, palladium catalyzed coupling reaction. Okay. So, most importantly synthesis of CsP2 bonds, right. Well, let us try to think about forming a biphenyl ring. Can this be formed very easily without invoking organometallic intermediate? I guess not. Can one synthesize this sp2 this sort of bond, or even this sort of bond? How one would think of forming these bonds remained completely under difficult situation. And of course, a number of drug molecule such as this, which I am trying to draw here, is a lipiter, where you see this is one carbon-carbon sp2 bond formation, and another, for example, this one another carbon-carbon bond formation, and you have a long chain of course over there for these processes. And overall CO2H, for example, overall these two difficult carbon-carbon bond formation reactions, this is lipiter, are carried out by doing the so called cross coupling reaction or palladium catalyzed cross coupling reactions. Now, of course, for cross coupling reactions, as you know, the reagent usually that is used is your organohalide reagent, right. For example, aryl bromide, aryl chloride, aryl iodide, of course nowadays this aryl diazonium or even aryl carboxylic acid. Usually you have a aryl halide that is used traditionally, and then depending on the other reagent, other coupling partner, the reactions are differing in their name, right. We are most familiar with, for example, Suzuki reaction, right, which utilize aryl boronic acid as the coupling partner. Now, once that coupling partner is changed, of course, aryl boronic acid in conjunction with aryl halide. Now, once the aryl boronic acid changed to aryl tin reagent, that reaction is called the Stille coupling, right. So, the other coupling partner keeping the aryl halide constant, if you change the other coupling partner, the name of the reaction, because those are the usual name of the reaction are changing. So, aryl tin reagent should be called Stille reaction, aryl boronic acid reaction Suzuki reaction. If one is using aryl zinc reagent, that is called Nigisi reaction. If it is a silyl reagent, aryl silyl reagent, that is called the Hiyama reaction. If it is lithium, okay, aryl organolithium reagent, and those are called Kumada coupling, right. Lithium or magnesium reagent is used, then those are called Kumada coupling. So, with all these name reactions, we will systematically discuss their pros and cons, where a particular this bond formation, carbon-carbon bond formation reaction good at, where they fail, what would be a ideal reagent that we would like to, or ideal types of reaction that one would like to use both in industry and in academia. Those are the one we will be discussing subsequently. Now, let us define those organometallic reagent and the name reaction, because those will be coming pretty often for our discussion. Let us try to nail it down. Okay. So, cross coupling reactions, this is some part we will discuss in detail. Cross couplings, usually it is a Rx, R is aldehydage, it is aryl alkynyl. Okay. Nowadays of course, even the aliphatic are used. Halide X partner could be chloride, bromide, iodo, OSO2, CF3 and so on. And the other partner, based on which the name reaction is changing to give you overall RR prime, is the one which is usually called the transmetallitic reagent. Let us say we are using palladium catalyst. Of course, we can use other such as nickel, copper, cobalt, etc. We need various additive depending on the reaction condition. Overall, if it is a lithium and magnesium reagent, that is called Kumada coupling. If it is boron reagent, that is called Suzuki coupling, right, Suzuki reaction. If it is tin, that is Stille reaction. If it is zinc, that is Nigisi reaction. And if it is silicon, that is the Hiyama reaction. Okay. Overall, then we have these at least 5 different type of reagent or 5 different type of starting material that is used, for example, palladium catalyzed carbon-carbon bond formation process. Now, overall there is a synergy, there is some sort of harmony among these all 5 different type of reaction. Of course, we will discuss separately this palladium catalyzed carbon nitrogen bond formation, or famously known as Buchwald-Hartwig type of coupling, and other reaction that is also under the cross coupling banner is the for Shunagashira reaction, for example. So, those we will discuss separately. Let us just simply we are trying to discuss these 5 reactions first, and then we will come to those other reactions which are extremely useful for industry as well as in academic setup. We will first try to look at if there is some sort of general mechanism for all these reactions, all or each of these reactions on their own right have caught the imagination of the scientist in terms of its application, it becomes really widely used at this point, but there exist a number of issues almost with every reaction. We will try to touch upon those and the development that has been carried out over many decades during our time that we would like to discuss. Before going into details, let us try to look at a generalized mechanism for all these processes. So, generalized mechanism. Okay. For these purposes, we will have a palladium reagent. As I was saying, it is not necessary to use palladium, but we will use palladium for a general mechanism. Mechanism is oxidative addition is the first step, okay, with Rx to give a ligand palladium intermediate where R and X are attached with it. From here we get Ln palladium R and R prime, where this R prime is coming from. This is where the transmetallating reagent, that is organoboron reagent, organolithium, magnesium, organotin, organozinc or organosilicon reagents are important. Here M and X gives you Mx. Overall in the process we get R prime as the product formation, that is the reductive elimination, and this step is called transmetallation. So, it is a oxidative addition, transmetallation and reductive elimination. So, these are the key approaches for these processes. Overall, we do see that we do have a process where starting from an intermediate, when we have a lower valent intermediate, for example, palladium 0. From there on, an oxidative addition with organohalide, for example, aryl bromide, gives rise to a palladium 2 intermediate, okay, at which now we see a transmetallation. So, after oxidative addition, transmetallation usually proceeds with the R and R prime, both the partner, carbon partner on the palladium, keeping the palladium 2 oxidation state intact. So, palladium 0 goes to palladium 2 during the oxidative addition, and during transmetallation palladium 2 oxidation state is maintained. Subsequently, we do see that this palladium 2 intermediate undergo a carbon-carbon bond formation, that means the product formation step between those two R and R prime. So, 2 sp2 carbon center, for example, undergoes reductive elimination to give palladium 2 to palladium 0 formation that regenerates the catalyst, and one can see the product formation, or so to speak, the carbon-carbon bond formation reaction that occurs subsequently. So, by doing so, we are able to show that it is a palladium 0 to 0 catalytic cycle. So, 0-2 catalytic cycle that is involved, and during these processes then during the transmetallation process usually one would need a base that we will discuss. For other metal, a similar +2 oxidation state, if it is a, for example, nickel 1, it could be nickel 1,3 catalytic cycle. Nickel is a little problematic case, sometime depending on the substrate combination. Actually metal mechanism can change. It is usually it is usually proposed to undergo a radical type mechanism, but nonetheless, it is a overall +2 oxidation state change usually gets predicted for these kind of reactions. But it is extremely difficult to put a single mechanism for all the type of cross coupling reaction that we do see, but the one we discussed usually captures the field, but not necessarily exactly correct for all the reactions. This is a oversimplified mechanism that we have drawn for all the different type of cross coupling reaction or carbon-carbon bond forming reaction we are going to discuss. We will discuss each of those topic in detail I might will be discussing briefly about 1 to 3 of these reactions and then come back and discuss these reactions in greater detail. Okay. We will start discussing briefly the Suzuki reaction, and then maybe the Nigisi reaction in a bit, and Stille reaction in the next class briefly. We might will again, after that we might will come back to these type of reaction in more detail to give you better idea about these processes. Keep studying these cross coupling reactions and their utility in the synthetic setup. Okay, bye bye.